So welcome. I think there's a lot of expertise here in Rome on neural networks, and I'm very honored to give this course. Two things. First one is feel free to interrupt me at any time if there's something is unclear, and so I'm happy to discuss that. I think it just makes these lectures much more lively if you just ask your questions whenever you want. The second thing is you can have also, I think it's good for a longer lecture if you're unsure about notation. So feel free to download the slides from this link. If you want, you can take now a picture or so. It's a long hyperlink. Okay, good. Ready? Good. So when I started this, I was very fortunate to enter this field. You want the slide? Yeah, sure. Final chance to take a picture now, or you can share it maybe. Yeah. And I will update it. I think I will add some slides during the week, and then for the next lecture you can get new slides. Okay, so when I started with this, I think the main obstacle was that 2014-15, when deep learning became a big thing, people just didn't believe in theory. Okay, so they said this is something so engineering driven, and so why should we actually do theory for that? It's just impossible to do that. And that was the big obstacle when I first said, okay, so I want to look into this. And what were the reasons for that? So people said, well, this is extremely, I mean, it's in neural networks, they don't really help if you apply to simple data structures. So the benefits, you can only see that for very complex structures, and those ones are too hard to analyze mathematically. That's one thing. The second argument that I recall from this time is, well, this is just neural networks in itself are maybe not so great. It's really the whole tuning that altogether that gives you a state-of-the-art method. So if you just fit a neural network of some arbitrary size, and so that typically never works, and there are engineers who spend years of their life trying all sorts of different things, and then they combine it with dropout, without dropout, with batch normalization, without, and at some point, each of them can maybe contribute 1-2% in overall misclassification, error, decay, and all this together, that gives you then something that works well, but the individual ones are not great in itself. So that was another one. Then all the things around nonlinearity is, of course, a huge thing. So in statistics, we like linear models, and then we understand everything. We can do explicit computations. Once it becomes nonlinear, then you can try to linearize, but in neural networks, it's not a good thing to do because the nonlinearity is somehow essential, and so then it typically gets very hard for mathematics to deal with that. You have all these other issues with the non-convexity of the function class created by neural networks, and also the other forms of non-convexity that can occur. And another reason is that these two AI winters that happened, one from the 70s and early till the early 80s, and then the second one in the 90s, they were both caused by theoretical results that were completely misinterpreted. So there's a bit of a reluctance in this field to believe too much in theory now, because somehow the whole field basically collapsed because of some wrong theoretical result. Or they're correct, but then somehow misinterpreted theoretical result. So that's another obstacle where I think people are quite cautious regarding theory. So why should you then come up with theory? And I think here's some reasons why one wants to do that. So ideally, we want to get some sort of understanding why these deep neural networks work in the way they do work. And another thing, which is, I believe now some retrospective view was quite important, is that after we published these papers, and so people came to us and said, because you have written it in this form, it was very accessible to us, and that's how we could understand what deep neural network really is about, right? So in these computer science papers, it's sometimes very, very chaotic. Things are invented multiple times and so on. And I think mathematics can play an important role just to to present this machine learning as a coherent field. So it's not about proving theorems, it's just about writing it down into, I think the mathematical language is very well suited. In the end, it's all linear algebra what they do, right? But that we can write it down in a coherent, consistent way, and then this is maybe also the way this can be taught to future generations. I think that's also an important thing we can contribute as mathematicians to this field. Once we understand it, I'll also show you some statistical results that really show that we can also compare to other methods and then can work out specific scenarios where one method performs better than the other, and that gives us some form of insight. A thing which is probably where we're not making any progress is this idea of, so you have to pick the architecture, which means the number of layers, the width of the network in each of these layers. And the idea was, well, with statistical insights, we might not be able to say exactly, okay, so this architecture, but at least to narrow it down, that we understand the scaling behaviors and so. And that is probably something could be too hard for theory. So I don't have any convincing, or I haven't seen any convincing theory that really helps in doing that. So it remains something very engineering driven and based on trial and error. One thing theory can be extremely strong is by detecting some limitations of deep neural networks where they are not optimal in a way. And that is something which empirical work is very hard, because suppose you train a neural network on a data set, it's not going to work. And most people will say, well, you haven't done it the right way, or just try harder, or take a larger neural network, or do something else. But with theory, we can really show that this is some impossibility results. And once you can show that, then you have to, of course, to do the right interpretation of that and not causing another AI winter. But based on that, you can come up with other ideas, right? So shallow networks were basically seen not to be very powerful, and then based on that, you can then propose deep neural network systems. And then another big thing, which is, for instance, solving inverse problems. So you don't want to do everything learned by a neural network, right? So in the end, it's about combining classical methods with neural networks and sort of hybrid methods that you use the classical inversion scheme. And then on top of that, you maybe do some machine learning. And to do that in the right way, theory can provide some insight if we understand when neural networks work well and when classical methods work well, and then based on that, design new methods. That's a bit the holy grail, say, of what a theory can deliver. Now, what do I want to do in this course? So the course is structured in these 4 bits. The first one, what we will talk today, is mainly about the first one, and then maybe a bit of the second one. So the first one is all about the theory for shallow neural networks with one hidden layer. And we will talk briefly about some theoretical results that show in which sense additional layers can be helpful. The statistical aspects, I mainly want to cover that on Wednesday, and then everything. So there's more on learning than the over-parameterization, all about the aspects of gradient descent and learning that will come on Friday. Okay, so here it's an empty slide. So what does that mean? Some parts I want to do with my pen. So I think and I want to start in the beginning, just a few minutes. I want to go back to the very beginnings of these neural networks. It's often not covered in courses, but I think it's quite insightful to understand why artificial neural networks are the way they are nowadays. They're quite abstracted away from the biological networks. So people in the 40s and 50s, they tried to model a biological neuron. And so one way to do that was to say, okay, there's these neurons that have a potential, and once the potential reaches a certain threshold, then they release a spike to all its descendant neurons. How do we model that? Well, we say, okay, so we have an input here. I need my pen. Okay, so we have an input x, which is, say, an r to the d. And so these inputs, each of them is reweighted. So that is also the case in the biological network. So we take a vector and take the transpose. So we form an inner product or scalar product. And then we add a threshold. So that could be also minus v, maybe better. And once that is larger than a value, then we the neuron should respond with it should fire, so that should give the value 1. So the whole thing is to say, okay, so the sigma of u, that would be then basically the sine function. So if, whereas for the 0, we also take it to be 1, and otherwise we take it to be minus 1, and that's it's just a shift. So you could say it should be 0 and 1 like this Heaviside function for a specific reason, which comes in a second. Let's just shift it such that the outputs are minus 1 and 1. But this is the function class. Function class because it's parameterized in this W vector and this V. It's just a real number here. Generated, considered by Rosenblatt in his 1958 paper. And the question now is how to train such a thing, right? So we have a class of functions that are parameterized in W and V. And so how to train this? And so Rosenblatt, he came up with an idea called the perceptron, and perceptron really refers to the algorithm. So perceptron works as follows: you have data, x1, y1 till xn, yn. And there also an RD times R, right? So there always an input, which is an RD, and a real response. Sorry, this is not real, so it's minus 1, 1. So it's a classification problem. So you have minus 1, 1. And so what you want to do is you want to find a function of this form such that if you stick in this xi, it should return yi. And if that is possible, that means somehow, if perfectly possible, that means somehow these two classes, they are separable by a hyperplane. And so the algorithm now works as follows. So you search so you initialize, right? So you take some W0 and V0, and then in one step you search for a misclassified example such that the yi is not equal to the f. Maybe I write it differently. At this moment. Okay, so those are the parameters at this stage, say W and V. And then we update these parameters. We update them as follows. We have a learning rate, eta, and then we take the label, the sign, and here the vector. So this is a d-dimensional vector. This is a d-dimensional parameter, so this is a number here. And we just update it this way, and we do the same thing with the bias. Okay, so this is perceptron, and then we do it until we don't have any misclassified sample left anymore, or some other stopping criterion. Okay, so now. What is this for an algorithm? So you can tell me how does it look like? I mean, what is underlying perceptron? Knows. So if no one answers, then I pick someone, right? So, touch style. Yeah, it's gradient descent. It's a form of stochastic gradient descent, right? So it's a huge stochastic gradient descent, and the question is only like for which loss function is that stochastic gradient descent. So this is a loss function that if this is perfect, I mean, if we encounter an example that is correctly classified, then the gradient has to be 0 because there's no updating is happening. And if the things don't match, the signs of these, the response and the predicted response don't match, then the gradient of the loss is given by that expression. Okay, so now we can work it out. And one way to work this out is to say, okay, let's introduce W tilde, which is just the vector where we put the bias as the last entry.
So what was it stochastic? Because you were taking the wrong yi's at random?
Yeah, so in stochastic gradient descent, you can go via epochs through the whole data set, right? And in gradient descent, you always compute the gradient based on the full data set. But here you see this is only picks one sample in the gradient computation. And so the question is now, how do you search for I? You can, for instance, say, okay, I'm randomly sampling from my training sample, or I go like in the modern way, we would say we go through the sample until we reach the end, and then we start again and search again until we converge. And that is then an epoch to go through the whole sample once. Yeah. Okay, so we have this, and then we also introduce these xi tildes, which is the same thing. Just the bias or intercept that goes as the last component into the vector. And then perceptron is just W tilde, gets updated by xi tilde, right? So the last one is the 1, and that gives you exactly this formula here with the 1 here. Okay, so the whole thing is the W tilde. Now, if we then reverse engineer and work out what is the loss here, so the loss in this case is so it's based on a generic, say for generic X input and a corresponding response, and this is the parameter, and I always have to check what is minus and plus, so it's minus y W tilde transpose X tilde, and then the what we now call the maximum or value here. So this means it's if this is the interior bit is negative, it becomes 0, and if it's positive, it's a projection on the non-negative axis. Okay, so that's the loss function. Because now suppose the sign of y and the sign of that one doesn't match, then this becomes first of all, think about them, they do match. So that means they're correctly classified. If they do match, then this is the same sign as that. So the whole thing becomes a positive number. And then with the minus, it becomes a negative number. So that means that becomes 0. And then also the gradient will be 0. And in the other case, if the sign of this thing doesn't match the sign of that one, then the whole thing becomes positive, and then we can just get rid of this and compute the gradient. And in this case, the gradient with respect to the parameter will be just this will be just minus y x tilde, right? And this is if y not equal to the sign of W tilde transpose X tilde, which is the same as saying this is the sigma of W tilde transpose X tilde. And this one is, of course, because now we write it, this is the same as this one, right? So with the xi in there. So this is the same one as that one. Because we have redefined the xi into this xi tilde by putting the intercept in there, and if you write it out, then we get the whole thing back. Okay, so now we have a minus here, but this is what stochastic gradient descent is. So you go into the opposite of you do descent, so you go into the opposite direction, so you have to put a minus. So the stochastic gradient descent would say, okay, you find some way to sample from your training set, and then you compute the gradient, and here you put a minus. You can also write it like this, so you maybe I write it like this. And then we can here write k plus 1 equals. Okay, so this is how this looks like. So, and tk, in the case iteration, you just pick an index. So this is an index that fits one of the elements, so this is always something in 1 to n, right? So it has to pick a sample, so that is some map, and there are all sorts of different choices you have. But this is how a stochastic gradient descent looks like. And so if we now stick in this formula, basically you see that these two things are the same. Okay, so that is just a specific way of doing stochastic gradient descent. What's interesting in this one, and this caused a lot of problems, and so later, is that you can define a loss that does not include the activation function, right? So the sigma, which is not smooth, which you, and otherwise would cause a problem once you form a gradient. If you would put a sigma here, then if you form a gradient, you also have to take the derivative of the sigma. If the sigma is a jump function, so then it's not going to work. But in the specific case of one neuron, you can get rid of this and just put something which does not involve the sigma here. Okay, so it's a specific trick that only works for one artificial neuron. And you still get to something reasonable, because the whole thing also has some statistical guarantees. And before I show you this statistical guarantee, I just want to show you how this perceptron works. Okay, so here are the data. So I color-coded these two classes. So those would be the class with, say, label -1, and this is the class with label +1. And so they are separable by a hyperplane, but there's very little margin between these two classes. So this is a hard problem then to find a separating hyperplane. And now if we run the perceptron on this data set here, then you see this is the number of misclassified samples over the iterations. One sec. So what you see here is this is not monotonically decreasing the number of misclassified, right? You can make updates that push you into a direction, right? So you are going in every update, you just change the direction of the hyperplane, and sometimes you make a bad one, and then suddenly you have more misclassified afterwards. But overall, it works well, and at some point you will end up with 0, and there's some mathematical guarantees that you will end up with 0. It's quite astonishing that you can prove something about this, because once you have non-monotonicity, it gets very, very hard, right? Because then you have to find something, some object underlying the whole thing, which somehow decreases, right? And that is hard, and it's really, really surprising that for perceptron you have a very, very simple proof actually to show, give guarantees how many steps you need in order to reach 0 misclassification error. You have a question?
Yeah. No, I have a question. Just an observation that this procedure is also called a support vector machine in computer science community.
That's true. So this is the thing that happened after the perceptron. So the field split, and these support vector machines are one generalization, and cellular networks are the other one. So support vector machines have additional slack variables and so on, right? So like in the loss functions. And so but this is true. So somehow this underlies all these developments of the support vector machines later as well. Yeah. So it's a very fundamental thing. But we will later go to the cellular networks direction. Yeah. Yeah. Good point. Okay, so this is perceptron convergence theorem. And I just copied it from my lecture notes. So what we have is we have n samples. Our training set consists of n samples. And what we assume is that there are also separating hyperplanes. So that means this is the condition. Okay, so we can find parameters such that every sample is perfectly classified. This exactly means this one. And now the difficulty, of course, is in this: if these two classes are far apart from each other, then it's easy, right? You can do it by eye, but also an algorithm should not take too many steps. So the difficulty should be depending on the margin, the distance between these two classes. And this is this gamma parameter over here. So this gamma parameter measures somehow like how close is the closest data point to the separating hyperplane. So if you have this as a solution, you can also multiply W star and V star, all the parameters, by positive alpha. You get to exactly the same solution, right? So this is up to a positive scaling these parameters, and to take care of this somehow we can divide here by the L2 norm of the parameter vector, the full parameter vector, and that gets somehow this avoids these problems and this non-identifiability of the parameters. And then what the claim is that if we initialize perceptron and these parameters and take the learning rate eta, then perceptron will converge, means have no misclassified samples anymore after that many steps. And steps means here updates, which means it's not STD steps. STD steps, right? If we write it like this in STD, then it's not the K here, because the K would also count the things where we don't make any update where the gradient is 0. It means really update steps in that sense, where we find a misclassified sample. Okay, so another way to say it would be it finds at most that many misclassified samples before it perfectly classifies this. Okay, let's look into the bound. It's clear that if the margin becomes smaller, the problem gets harder. You get the 1 over gamma squared here. So if gamma is very close to 0, that makes it take longer. Another curious thing is the dependence on the learning rate. So you see, for instance, if you initialize at 0, then the learning rate disappears. So it doesn't matter what the learning rate is. It's a very strange phenomenon. You can make the learning rate 1 billion, which means in every step you make huge changes, and it doesn't matter. So you still get this guarantee. So it's a very strange phenomenon here. Also, if you make your learning rate extremely small, so here it's all with constant learning rate. Yeah, the size, whether this is really sharp, I don't know, but the size of these xi's, that somehow also matters in the bound. Okay, but you don't see any. What is interesting is it doesn't really matter in terms of like how large a sample size is, right? You would think maybe if my sample size is a million or so, it takes me longer, but there's no n dependence in this bound. So it's in many cases very interesting result. You want to ask something?
Success and the minimum can change if n is large.
That's true, yeah. So if you would think about somehow they have an underlying distribution or so, then there must be always one thing that gets closer and closer to the decision boundary, and then somehow gamma will go to 0 with n with the sample size, and then you get some rate in the end. Yeah, that's true. Okay, so I didn't include here the proof because I don't want to spend too much time on that. But the proof is also interesting. So maybe if you ever want to look at it, I recommend to do this once, because I mean, how would you prove perceptron convergence, or how would I prove it? I would try to understand how these iterates that we generate, so we generate here iterates in this update scheme, and then I want to compare, typically like what everyone would do, compare how these W, how close they are to the true ones, right? So you assume that there are two parameters that can solve it. There can be a larger set, but say you pick some, like a smart choice of two parameters, and we want to show like that these W's get closer and closer to the W star. And at some point they're so close, and it's good. A perceptron convergence theorem proof is very, very different. So what it controls like how far you move away from the initialization with your iterates. And then you derive a lower bound for that and an upper bound for that. The lower bound depends quadratically on the number of updates that you make. The upper bound depends linearly on the number of updates that you make. And because the lower bound is quadratic and the upper bound is linear, so that if the number of updates that you make would be too large, you would get a contradiction, and that gives you then the upper bound. So it's a really, really unconventional proof. Also beautiful, also quite intriguing how people came up with this. And that somehow also can deal with a hard problem, because if you have non-monotonicity in some aspects, like the number of misclassified samples, which is here the key objective, then you have to come up with somehow also non-standard ideas. Okay, so now the thing is, how can we generalize that to go beyond one neuron? And so the next idea would be to say, okay, we introduce these cellular networks. And cellular networks is now, before we just had m equals 1, and there was no Cj here. Now we can build m of them, and we can weight them by additional parameters Cj. And that is then the definition of a cellular neural network. And later we write it as m is the number of units in the hidden, so-called hidden layer. And so what was the problem with this is you don't know how to train it. So the perceptron doesn't have a clear, or no one ever could find a good generalization to several neurons. And that has to do with the fact that once you have several neurons, you somehow always have to involve the sigma into the loss functions. With one neuron, somehow you miraculously can avoid that. If you have several ones, you have to include it, and then if it's not differentiable sigma, so then you're screwed. There's nothing you can do if you want to do some like gradient, stochastic gradient descent thing. Another thing was this book by Minsky and Seymour, which is also covers this perceptron convergence theorem, and they make a very strong point in their book, which is called Perceptron, actually is the title of the book. They make a very strong point that you cannot represent this XOR function with a cellular network with these activation functions from the perceptron. So what is the XOR function? It's a logical function, which is the exclusive OR, right? So it just has 4 points. On these 2 points, it's sorry. This function is 1. On those 2 points, it's 0. Yeah. So and there's no way to even if you have to perfectly represent it. So you can make approximated, but you cannot perfectly represent this exclusive OR, which is a basic logical operation, with a cellular network with these activation functions that we considered before. And based on that, they said, well, these neural networks are not expressive enough, right? So they come to something very elementary. And that has led to this first AI winter, where this is a theoretical result, right? So it's where funding suddenly decreased, and no one was interested in neural networks anymore for a whole decade. Although in their book, if you read it, in their book they show that with multiple layers, you actually can represent it. but the idea was, okay, multiple layers is just far too difficult to train, since they didn't know how to train shallow networks, right? So multiple layers was even a level of abstraction higher, that people gave up on this idea. That's a bit sad, because we will see this is not a big obstacle, this XOR function. Okay, so then let's go to the 80s. And then what do people do if they understood, okay, so we basically all this, what underlies the perceptron is sort of gradient descent or stochastic gradient descent. And we can just smooth the activation function a bit, right? So instead of taking something that goes from -1 and then jumps exactly to 1, so why not smooth it a bit, and then it becomes differentiable. And here this hyperbolic tangent function is just such a function.
The result by Minsky holds for the heavy side activation or for any activation?
It's for the heavy side activation, yeah. Yeah, exactly, yeah. So back then they didn't look at anything else than heavy side activation function. Yeah. And so this idea came only once the link with gradient descent and so on, and then you can say, okay, if we need the differentiability of the sigma, then just make it differentiable by smoothing it out a bit, the -1,1 function, or if you want, you can also do it like heavy side, and then you go from 0 to 1, and then you end up with these so-called sigmoidal activation functions, which are all smooth version of the jump function that goes from 0 to 1. And then in the modern literature, you all know this, of course, we have value and CLU and leaky value and all these sorts of things. They have a different flavor, and this only comes then with the start of the deep neural networks later. Okay, so now let's look at these shallow neural networks and think about sigma as, say, one of these activation functions. So one way to interpret this class is, here we have in the first, this is basically what the layer does, the first layer, the output of the first layer, we can learn features, and then in the second layer we just have, based on these learned features, which cannot be anything, they have to be of this form, right? So somehow adapt these parameters in some specific way based on the data set, and so that gives us a large range of features that we can learn, and based on these features, we then in the second part we just do a linear expansion of them, right? So that's the idea. And then from there we can now go to the deep neural networks, and I just want to introduce here this notation that we will use, and that help a lot, I think, to understand how these neural networks work. And so what we do, first of all, we to get somehow a nice notation with these shift vectors. So if we have a vector of length r, then we say the activation function with index v, that means this is a map from the vectors of length r to the r-dimensional vectors by subtracting component-wise these entries of the shift vectors, and then applying also component-wise these activation functions, right? Activation functions are always univariate functions. And now what we can say is, we can say a neural network that has depth L and width P, where the P is the vector that has length L plus 2. So the depth refers to the number of hidden layers. There's no convention. Some people also would call the number of hidden layers, would call L plus 2 the number of layers or so. But the most common notation nowadays is really L is the number of hidden layers. So then we have an input and an output layer. So overall we have L plus 2 layers. Each of these layers has a width, a number of neurons. Number of input neurons is in P0, number of output neurons is in PL plus 1, and then the L numbers in between, they refer to the width of the L hidden layers. And now in your network with this architecture, right, the architecture is given by the depth and the number of units in every layer, so that's the architecture. And your network is any function of that form where we take as input a p0 dimensional vector. This is our input vector. And then we multiply with the p1 times p0 dimensional weight matrix. So that's a mistake. Should be the opposite. P1 times P0, so that gives us a P1 dimensional vector here. Into this P1 dimensional vector, we apply this operation. So we subtract the shift vector and apply component-wise the activation function. So that again gives us now a P1 dimensional vector. And now we have a P2 times P1 dimensional matrix. We do matrix vector multiplication, and we do this shift correction and apply component-wise the activation function. So you see just alternating between the matrix vector multiplications and component-wise application of the activation function, and in between there's always these correcting for the shift vectors. Okay, so this is the algebraic formulation of that. So these network types are also called feed-forward networks because the information flows from the input to the output in one direction. So the architecture, the L and the number of layers that is given, right? So you pick one, and then the things that are learned are all these parameters, and the parameters, those are the entries of these weight matrices and also the entries of the shift vectors, and that's in the practice can be in the millions or billions and so on, right? So it can be very large matrices and many parameters to be learned. So if you like to rather these graph representations, then one can write these functions. You can write them as a graph. Every node in the graph represents a very simple algebraic operation. It takes just the outputs of the previous layer, weights them with exactly the way we wrote it for the perceptron, weights them with a weight matrix, with a weight vector, and has this bias term in here, and then applies the activation function that goes then into the signal that is used for the next layer. And this is exactly one-to-one. So whether we write this in this algebraic formulation or as a graph, that's the same. So that would correspond to a neural network that has architecture 4, because we have here 4, 3, 3, 2 as width vector. The number of hidden layers is 2, so the L would be equal to 2. And so sometimes it's more convenient to write it in this form. Sometimes the algebraic notation is much better because it's much cleaner and we can use much more the tools from linear algebra. Some notation here. So if these matrices are sparse, then we call them sparsely or sparse networks. And the brain is sparsely connected, and it's also very much abstracted away from the brain. In practice, all the networks are deep, but there is certain theoretical advantages of sparse networks, and we will come to that. So this is an important object. The second thing is if it's not sparse, then we call them a dense layer. If WI would correspond to a dense layer, or all the layers are dense, then it's a dense network. Shallow networks is by definition it's L equals 1. So in this case, you can, as a specific case, you can derive this formula that we had before, right? So we wrote this formula here. This one. So if you just rename these parameters, right? So then we take those are the rows of the W0 matrix. This is the first shift vector, and this is the second matrix. W1 matrix is in this case just a vector with these components. Right? So that's exactly the same thing, but for shallow networks, it makes sense to write it in the specific form. Now, if you change the task, then you also have to change the network structure. So if you want to do classification, you want to make sure that the outputs that the network produces, that this gives you a probability vector, the probability to end up in these classes. So the number of output neurons is the number of classes. If you have 1,000 classes, so then you have 1,000 output neurons, and the thing that the neural network spits out is a vector of dimension 1,000, a probability vector. In each entry, you see the probability, what the network thinks that input is in that specific class. And to achieve that, one just puts here the so-called softmax function on top of the structure. Okay, so that obviously transforms whatever comes out here into a probability vector. And in this sense, what you can see is that these neural networks, they are really nonlinear extension of linear regression and logistic regression. So if we do classification and we get rid of all these hidden layers, right? So then we basically just have W0 in here, and then this is just a logistic regression model that we fit to our data. If we have linear regression, so then we don't have the row here, then we just have basically W0 times X and just linear regression. Okay, so by adding hidden layers, we make it nonlinear. And this is also the reason why the linear model is often a good model to study something like some regularization technique for deep neural networks. So this is something which we still can, which is still somehow tractable. And it's, one can always argue it is a specific, like a degenerate neural network in a way. Okay. And then these feed-forward neural networks, this is the thing that is studied a lot. Maybe what I would like to encourage people is thinking about theory to study other structures, right? So the ResNet became very important. So it has also built-in skip connections, which always pass the identity forward. So here, these networks can become very unstable with depth, and the ResNet, because you center around the identity. So if the parameters are basically all zero, and you just map the identity, and that's a more stable object. So then, like, this was a huge jump, and before for deep neural networks, one could maybe train 20 layers, and so on. Once this ResNet architecture was introduced, the number of layers jumped to 150 and more. Most of the early state-of-the-art results, they were obtained actually from convolutional neural networks, which take these invariants under shifts of images into account, right? If you classify objects, cats versus dogs, objects classification on images, then it doesn't matter whether the cat sits in the corners of the image or somewhere in the middle, it's always a cat. And they have these built-in thing in the convolutional layers, and that matters a lot. So that is very, very essential for the success of deep neural networks. There's not so much theory yet for them. Once it comes to everything with text, first we had recurrent neural networks, then these long short-term memory networks, and now the transformers with the attention layers. There's even, I mean, people try to, because of the success of LLMs, do more and more on transformers, but there's also remains still a lot of stuff to be understood. Very important thing, and like one of the claims is also that the success of the deep neural networks really sits in these additional structures built on top of the feed-forward neural networks. Still, the feed-forward neural networks are interesting objects to study. Now, what are the challenges then? What are to study, let's say, from a statistical point of view? This is a very old plot, more modern ones, but so you see back the time when I started thinking about these theory for neural networks. Here you see the number of parameters of these neural networks back then in terms of like the size of the disks, that's how large these networks are. For instance, the famous AlexNet has 60 million parameters, so it's somewhere here, and there were also back then already ones, these BGG networks with more than 100 million parameters. But on the other side, the number of training samples is smaller, so it's really a high-dimensional learning problem where there are more parameters than samples. Okay, now briefly about the learning. We will come back to that also later on Friday. So how do we fit now such a neural network to data? Well, we have to, again, like for the perceptron, we have somehow to identify a loss function, and then we do a gradient descent method based on this loss function. And so how do we define a loss function? Which depends on the problem that we have at hand. So if we do classification or regression, then that changes the loss function. The most common thing is to do the so-called cross entropy loss. and that coincides with the negative log likelihood. So in a way, we do maximum likelihood estimation over the class of network parameters. Of course, we are not able to compute the MLE because it's a non-convex problem. We are not able to find the global minimum. In the case of, or it's like a pseudo, because I mean, if in regression no one believes this is Gaussian noise or so, but we just take the likelihood then from the Gaussian model and then train least squares loss on, and then based on that we do some form of stochastic gradient descent. Yeah, that works surprisingly well, and that was maybe nowadays we think about, okay, that's the gradient descent is just the standard, but when I first heard about neural networks from a colleague, so the surprising news back then was that something as cheap as stochastic gradient descent can work for these models. Because if you look into all the textbooks on optimization, then also the theory for optimization is all like second order methods, like Newton methods with Hessian or information about the Hessian and so on. They have exponential fast convergence rates, which they call linear rates. But like things like gradient descent and stochastic gradient descent, they have typically some not good theoretical guarantees. So it was quite a surprise that first order methods, just gradients, are so powerful that they are good enough here, and we have a lot of understanding of them as well, that we can say why that works so well. Now, what I want to do first, before I come to the learning, it all underlies also the statistical part, the question like how many, like which functions can you express with these neural network functions, right? Or approximate with them, because if you cannot approximate them, you cannot learn them, and then it's over, right? So if there's somehow holes in your function class that you can never reach with a neural network, well, then there's no way to learn such a function as independently of how well your algorithm is designed, right? You're not able to reach them. So the most fundamental question is therefore the question about this approximability. And so it is a strange function class. If we just look into cellular networks, then this is a really weird class of functions, because the argument sits in here, right? Here's the x. And for instance, you could ask yourself, suppose I have two inputs, like my input is b is equal to 2. How am I able to, with this class, am I able to find a cellular network that does approximately multiplication? Multiplication is one of the most fundamental things on Earth. But because these inputs, they can't interact with each other, right? They only can interact with the weight vector, which is not x-dependent. So it's just something we can learn. And then there's this sum over here and the nonlinearity over here. But it's not that we can somehow multiply inputs in the network structure. It's just not there. And then the question is like, yeah, does that now require a million neurons to somehow approximate it, or can we do it maybe very, very efficiently? And many important questions on the line. And maybe if you're bored by my talk, you can just try it yourself how to do that. So that's a nice answer. Okay, so one thing we can see, we can index these function classes, right? We're not interested in these parameters, right? So it's important thing for learning is like which functions do you generate. So and for everything else, for gradient descent, it's all formulated on the level of these parameters. But the thing is like, what type of functions does it generate? So we index these function classes by the number of units in the hidden layer, the M, which says like the complexity of the function class, and the activation function also plays a role, the sigma in here. And so this class has M times d plus 2 parameters. So you see the more units we allow in the hidden layer, the more neurons we allow in the hidden layer, the more parameters we have. Of course, they also include each other. So the larger we make the M, so the more expressive these function classes become. And now the thing is that we say a cellular network with the activation function sigma has the so-called universal approximation property for any a positive epsilon on any continuous function, we can find the number of units that is then allowed to depend on the function we want to represent and on the level of accuracy epsilon, such that we get subnorm approximation on a compact, let's say here the cube 0, 1 to the d, that approximates it up to level approximation error epsilon in our class of shallow networks. Okay, so this is the function we want to approximate, and that means there is an element in this class of shallow networks with m units, such that we get epsilon close and subnorm distance. Now I can ask you, do all activation functions have universal approximation properties? So you all notice. So which one doesn't?
Polynomial ones.
The polynomial ones. Why is that the case?
And because they produce a closed set, so it's not dense, super norm.
Exactly, yeah, right. So you just produce polynomials of the same order with that, right? So you can't do anything else than that. And so the interesting thing is that there is, no, I have to check it. Okay, put a lot of, okay, so I was here to put the proof for the universal approximation property. So they are basically the only ones which don't have that among the ones which have some form of regularity. And so here's one way to see how it works for the other ones. So you probably know that if we have a function, say g, then we have t plus h minus g of t over h. So this gives us approximately the derivative of g prime of t, right? So that's how we can define the derivative if we let h tend to 0. And now what we also can do is we could in principle sneak in here an x, and so then we would have to multiply here, and that would also still be true, right? And now we could multiply this here, and the g prime, we can multiply it here, such that afterwards we get, and now let's call the g sigma, we would get that sigma of t plus, say, let me write it this way, h times x minus sigma of t divided by h times sigma prime of t. This is approximately x if h tends to 0. Okay, so we can do the identity, approximate that, but we can do the same thing with second order differences as well, right? So if we have second order difference, then we have sigma t plus 2hx minus 2 sigma t plus hx plus sigma of t over h squared sigma prime prime of t, and this will approximate x squared. Okay, so it's the same idea, but just taking second order, the formula for the second derivative, and then we write everything, and then we end up with this one here. Okay, so that means now we have a way to represent x squared with this. Why is that interesting? Because what is on the left side is just a shallow network, right? So why is that a shallow network? Maybe I just show it here on this slide. So we have input x, and then in the first layer we compute sigma t plus 2hx sigma t plus hx, and here we compute sigma t, so here we have to multiply the weight parameters in h, and here the weight parameters are 2h, and now we can over here. What do we need for the outer one? Well, we need to get to something which is approximately x squared. We have to multiply with these weights, right? So this one will get to the weight. We put it here. We get 1 over h squared sigma second derivative times t. Okay, so we get here 1 over sigma prime prime of t h squared. Here we get minus 2 over sigma prime prime t h squared. And here we get 1 over sigma prime prime t h squared. Okay, and then we get here something that is approximately x squared. And that gets better, this approximation, if we send h to 0. Okay, so we have now found a new cellular network construction with, right, so this is the cellular network. Now we use graph representation. We have put down all the weights such that we can approximate the x squared. It has 3 hidden units. Okay, and we can do the same thing to approximate all powers. And we can also do something like x1, x2, because if we want to approximate, instead of x squared, we want to approximate x1, x2, then we can take finite difference operators with respect to different variables. And then you can somehow verify that if you do this, h times x1 plus x2 minus sigma t plus h times x1 minus sigma t plus h times x2 plus sigma of t over h squared sigma prime prime of t, that this approximates x1, x2. Okay, so that means here you, instead of having only one x for the first discrete differentiation, you do that with respect to x1, and the second one with x2, and then you just work everything out and reorder the expressions, and then you can see that. So that means you can get all the monomials by the same argument. Okay, so the higher the monomial, the more units you will have to put. I mean, here we need 3. If we want to do this, we need actually 4. 1, 2, 3, 4. And that makes the networks wider. But if by allowing, right, the cellular network allows us to make the width as large as we want. By making all the, we can generate all these monomials. I can approximate all monomials. And there's something to be worked out. Okay, so because now we want our approximation, of course, to be in L infinity 0, 1 to the d. And monomials, I mean, things of this form: x1 to the power a1, x2 to the power alpha 2, up to xt alpha d, with alpha 1, alpha 2, alpha d in the natural numbers, including 0. And there are certain things that are happening here. First of all, the networks have to get wider the larger the sum of the alpha 1 to alpha d. The next thing is we need the derivative to exist. So if we have something of order 2, then we need second derivative here to do this argument. If we want to do this, we need that to ensure that this sigma is alpha 1 plus alpha d differentiable. So the whole thing only works now for infinitely often differentiable functions. And the final thing is we need that this thing that we divide by has to be always non-zero. So that means we need to, the t otherwise doesn't play any role, right? So it's just one point that we pick, but we just pick, there has to be a point t such that the derivative, it has to exist and it cannot vanish. And this is exactly the reason why polynomials don't work, because they vanish everywhere after certain number of derivatives. And so that's exactly where this argument comes in, that this cannot be a polynomial. And then one has to show, okay, so one can do this in L infinity, and if we can do all the monomials, then Stone-Weierstrass theorem tells you that this is dense in the space of continuous functions. Okay, so then you can do all the continuous functions, and then you have proved a universal approximation property for that. Now, do you like the proof? I would say, okay, good. Then we have different opinion. I don't like it, because I think there's many strange things going on here. So, for instance, in this construction, you see that there's some, in the first layer, we make these parameters very, very small because we have to take basically the limit h to 0, right? To make it as precise as we want. And so that means first layer, very small parameters, second layer, the parameters go to infinity. And they have to cancel each other out, right? So otherwise we don't get exactly to x squared. So if we make this a bit larger or so, and this cancellation cannot happen. And so that's something very, very unstable that is probably impossible to learn by a method, right? Because otherwise these other order effects, they will play a role and they will completely dominate the x squared and make the whole thing go to infinity. So gradient flow can learn that probably, but once we go from gradient flow to gradient descent, if we have some form of discretization, then all these things get a bit differently discretized, and then this cancellation that is happening here is not going to work out anymore. Okay? So that's the thing. So it's not a learnable thing. The second thing I don't like about this is that it's completely local around a point t. Okay, so it only matters, right? So it's 2hx, it's small because its h is small and x is in 0, 1, so the whole thing is still small. So it only matters how the activation function behaves around sigma of t. So it completely zooms in into the local properties of the activation function around 1 point. This is the thing that's happening here. So you, in the first layer, you zoom in, it's making parameters small. In the second layer, you zoom out, making parameters large. But this is not how we experience activation functions, right? So the global properties of the activation function, that should matter. Now you could say, maybe for every monomial, so we need a different t, but it's not true. I mean, many functions have just, you can pick the same t for all these. All the thing you need is that there is one t that none of the derivatives is 0, right? So that's the case. So that's not the issue. So you can actually pick the same t everywhere, and that's also why I have this very sharp transition between polynomial activation and non-polynomial activation function. So if you have a polynomial activation function like x squared or so, right? So this is activation function x squared. Everyone knows this is x squared. So, and now I do a little perturbation of that, a smooth perturbation, but say here I put this. Okay, it should still behave like x squared. X squared is very limited in terms of expressivity because it just can do quadratic functions. But the universal approximation theorem will tell you that once you put this on top of them, like now do this instead of the red curve, then you can represent all the continuous functions, right? So you suddenly get the full universal approximation property, and that's very strange because these local things should not matter that much, right? So in practice, you would expect if I perturb my activation function a bit, the properties should more or less stay the same. So that is another thing, weird thing about these proof of the universal approximation. And here I just have put all the comments on the proof next to each other. I mean, I didn't give you the full proof, and it's also not maybe so important to work out the other details. First of all, we have an explicit construction, right? So if you give me a function, in principle, we could work out what that exactly means in terms of parameters, because we can approximate the function by monomials or polynomials, then we know how to approximate each monomial by a shallow network. So we could write down an explicit shallow network that approximates it arbitrarily well. But it raises the question, if we just trace everything back to approximation by monomials and polynomials, why not starting directly with polynomial approximation, right? So that would be easier in a way, and we could just do polynomial approximation. That they also have universal approximation property because of Stone Weierstrass. We don't have to prove anything. We would get rid of one layer of difficulty because approximating the polynomials is already hard for the shallow networks, right? And so that doesn't explain anything about neural networks because it just shows that they can do what polynomials can do, and polynomials are not a great scheme for approximation theory. So it's known that because of their non-locality and so, it's just not. I mean, they have like splines or weightlets that have much more favorable properties. And the other thing which I mentioned here and I highlighted here is really one of these problems with that, and many subsequent work in neural network theory has the same problem, that some parameters get very small and some parameters get very large, and you look basically at the limit here, and that's the thing. Can that be learned? It's a difficult thing because there are some things we know for classification that neural networks, the norm of certain weight parameters will explode, so that happens as well. But for like regression problems and many other problems, it's actually typically these parameters stay very, very small when they don't explode. Yeah, so then this one thing is the zooming in. This is the same here and here. That already is enough for the universal approximation property. So you don't look at the global properties, you just look at local properties of the activation function. And that seems not the right thing to understand neural networks. And then there are other ways. I mean, here we used the activation functions, which are infinitely often differentiable. Value, for instance, is not as just continuous, and you can still prove it because what you can do is you can show that if you convolve an activation function with a smooth kernel, and this is you can approximate this convolution. It's an integral, you approximate it by a sum, and so that means the sum can be represented as a shallow network, and so that means in the closure, in the span of these shallow networks, that includes also the convolution, and then you can work later somehow trace it back to the universal approximation property with infinitely often differentiable activation function, because if you convolve an active function with a smooth kernel, then it becomes C infinity. So that means the only thing you have to show is that you don't end up with a polynomial after the smoothing, but you can basically, in the case of continuous functions, have just one additional step and then argue similarly as for the C infinity functions, the proof I have somehow sketched. The only thing that comes in here, if you do the smoothing, then the whole thing becomes non-explicit, so it's not clear how to come up with really clear constructive proofs for specific functions. If you have that for values, so it would be interesting to work out like what does it exactly, if you want to multiply x1 with x2, what does that mean in terms of value functions? Write down a nice constructive proof, but that is very hard because of the smoothing side. And you can also do it for monotone activation functions, which are just monotone, like heaviside activation function, universal approximation also holds, and so that can also be done along this line. So nowadays I still see papers sometimes where they say because of the universal approximation property, neural networks are great, and that's absolutely not the case, because universal approximation property is somehow the weakest guarantee that you can imagine, that you can somehow reach all these continuous functions and adding more and more parameters to your shallow network. But it's definitely not something that distinguishes neural networks from other approximation schemes. For that, what we will do in a second, you really have also to look into like how many parameters do you need to approximate functions to a certain precision. That is very important, this complexity of the class compared to the precision that you can achieve. And that comes in a second. I just want to mention that most of there are hundreds of proofs probably by now for universal approximation property. I just saw some new ones appearing on arXiv last week or on the weekend. So the classical ones, they don't do as I presented it, they mostly do the universal approximation property first in one dimension. In one dimension, it's basically simple, because then the scalar products that you have, they're just multiplication with numbers. And for instance, for value in one dimension, it's obvious because it's just piecewise linear functions. It's one-to-one, like every piecewise linear function you can rewrite to a value in one dimension and so on. So there's one-to-one. So it's clear. And the advantage of doing it this way is that once you have proved it in one dimension, then afterwards you can decouple it from the activation function, because afterwards you can just study like how well can you represent functions, multivariate functions, by rich functions. And rich functions are functions of this form where they have the scalar product in there, but these DJs can be, you can pick them. Okay, that can be your function system that you like, because basically you rewrite this whole thing into a double sum, where in one sum you approximate the tj's, which are univariate functions. You have shown the universal approximation in one dimension. You approximate them with the with that trick, and then the other part is basically taken care of by showing that functions of that form can approximate. So here's an equality, so it should be approximate if you make the m large, that you can represent these any continuous function f with more and more accuracy. Okay, so if you do that, now there are many schemes that you can do to do the second part. For instance, you could do Fourier transform. For instance, if you write Fourier transform, right? So this is Fourier transform, inverse Fourier transform can be written more or less the same way. Minus becomes plus. You all know this, you know, also Fourier inversion theorem. Now, if we rewrite a complex number into this form, then for the Fourier transform, if you apply the Fourier transform into the phase and the absolute value, then you can write this Fourier inversion theorem, this thing, if you rewrite it as this interior bit, and this one you use this one, so then you end up with this one here. And if you now work out that you only need to, because f is the real value function, you can put the real part, and you can interchange it with the integral, so you can put it inside, and then this becomes the cosine of that thing. And if you write it like this, you see now exactly the sort of structure that we have for shallow networks, right? So here we have the scalar product, and here we have a bias term. It can also depend. I mean, we can make it dependent on the w's here. So if we just by discretizing this integral, you get a way that shows that you can, right? If you discretize maybe a Riemann sum, and the Riemann sum approximates this f arbitrarily well, and that's a way to prove this the second step over here, right? So that's a thing you can do. And if you do that, the thing is, if you go to from just universal approximation to convergence rates, then you need things where you can really quantify bounds. Right? Universal approximation is just quantitative, but if you want to do the rates, then you need to quantify the bounds. And that's one way where you can get decent rates out of this construct. Okay, you do universal approximation in one dimension, and then this one afterwards. So also other ones you can also do Radon transform as the same thing. You can also put rewrite a Radon transform that's such that you get in the interior you get this an integral over these rich functions. Okay. And then there are also proofs for universal approximation that are completely abstract, for instance, by Hahn-Banach theorem and many other ways to show it. Now, I want to go now to approximation rates, and I want to split it in two parts. So the first part for shallow networks, also shallow networks at the moment. So the first part will be just like how well can a shallow network approximate infinite wide shallow network, which then in the infinite width limit we can imagine then if this converges somehow to something, then it has to be an integral of this form, right? Or shallow networks can be viewed as Riemann sums of that thing, right? So they are discrete, and we want to see like how well can it approximate such an infinite width object. And then once we can have understood this part, we can then wonder like how well can an infinite width network, so I call them infinite width networks for the reason that they occur as limits of making the hidden layer wide. How well can functions of that form approximate functions that we know of, like functions, Lipschitz functions, Hölder functions, functions in the Bezoff class, or whatever, right? So this is then two steps. The first one is the sampling step, say, where we go from the discreteness of the shallow networks to the integral. And then the second part is like how well can we, from this integral representation, then go to and derive function approximation for known classes. And known means like the standard smoothness classes that we like to work with. Okay, so one thing one can do is one can integrate out the C here. Okay, so here I have shown that so the C is quite unimportant, and it can then be replaced by some function that just depends on these on the weight vector here in the v, and then we only have to integrate here over one parameter less, which is good because the more dimensions we can kill, the better. And so this is then we're written in this form, and the interior one is just, and this function is then given by this integral. Right after we've written the probability measure in that form. Here, okay. Now for specific activation functions like value, you can even go a step further. I don't use that here, but I just want to mention it's a very, very important identity actually that comes back in many, many places in theory for neural networks. So if you have value activation function, you can actually use this identity here as well. So it's just a first order Taylor approximation of this function, and this is the second order Taylor, the Taylor remainder term. So it's just different ways to write down the remainder term. That's one way. And if you look into here, you see this is where the value function occurs. And so you can use that to integrate out actually the v here in this formula as well, such that you only end up with the integral over the w, which again makes it easier. The v is always a bit problematic because once we are like in the so that it occurs a bit of non-symmetry and so on. So you would like to get rid of it, and it also again reduces the dimension of this integral. But since we work here now for general activation functions, I just I'm not going to do this. I just want, before you blame me, I just want to show you that I do know about this stuff. Okay, now one thing which is easy is to get the rate 1 over square root of n, because that is just, I mean, we know this is just a central limit theorem type thing, or estimation rates in statistics. If we have an integral and we just can sample from it and then Monte Carlo or so, and then based on that get the rate 1 over m in squared norm or 1 over square root of m rate if we sample m times in the non-squared norms. So this is a general theorem that we can later apply to these shallow neural networks that says if you have a function that is integral over a parameter theta, and it's a probability measure here over the class or the parameter space capital theta, then we can take any measure q here, and we can exist a function that just has m elements that will later be our shallow network, such that we can approximate this integral here up to rate 1 over square root of m. And there's an important thing here, which is just a constant, but later will be important. Maybe Jeff will remember it already. Like there's also the norm of the g plays a role. Okay, so the norm of the g comes in here, and so we have it's a function in theta and x. So in theta, we take we integrate over the p, and x we integrate here. We take a measure q and we integrate over the q. Okay, so how do we prove this result? Just give you the ideas. It's a very basic thing. Is you just sample. Maybe I can put it actually here. Sample m point xi1, xim. Sample them IID. It's a probabilistic proof, which is nice because it's an approximation static statement. IID from the measure p and on this probability measure, and then what we do is we take here these theta j's. Okay, now we don't take the theta j's. We look at the f at m, which is 1 over m, j from 1 to m, g psi j, and that's a function in the second argument. So those are the psi j's that we sampled here. Now, and that's, or maybe let me write it here, some function in the x, so it's even more clear. So what's the expectation of then? the expectation of this thing, it's unbiased, right? It's just f of x, right? Because if you take the expectation with respect to that, you get exactly to this thing. So it becomes, and then the 1 over m and the m that cancels out, so it becomes exactly f of x, an unbiased estimator. And what's the variance of f hat m of x? Well, this can then be bounded by 1 over m, the squared thing here. Okay, so this is the exercise. So 1 over m, so that I guess you have all seen this before. G and then these L2 norm p q square. Okay, and now the wait, this is not over the x, because the x is fixed. So this is only for fixed x, and the x is the q. So it's only this thing, right? So it's, sorry. Okay, I should. So it is g theta x squared dp theta. Okay, and then if we now work out what is the expectation over f minus f hat m in L2 q squared, then we get this is smaller than, because we can, in statistics we call that the mean integrated squared error, what is in here, and the mean integrated squared error can also be written as the integral over the mean squared error, and the mean squared error can be decomposed into squared bias plus the variance, the bias variance decomposition. So that means this thing can be written as the integral over the squared bias, which is 0, plus the variance. I'm used to present it to statistics audiences if you don't. So and then we integrate dqx, and then you see this becomes then the GL2. Here we have this q squared over m. So and then the only thing that remains is, well, if this is an expectation, there exists also a realization that has that one, right? Because if there's no such realization of psi j's that do that, then it can also not be true in expectation. So therefore we get a deterministic statement from that there exist somehow these theta j's. Okay, we don't know how to construct them, but somehow if we sample that, then typically we should get them. And that also shows that to get this 1 over square root of m, right? These cellular networks, they have this additional thing compared to standard function schemes, that they have this first hidden layer which generates features, right? In the second layer we do linear expansion of these features. And the question is always, if we want to show something that cellular networks are cool, then we have to show that somehow the feature learning is important, that picking the features, this is something which we cannot do in the other methods. But here you see, because if we just sample, we will get something that has this rate, right? An expectation, but like a typical draw will have this property. And so that means the feature learning is not important to get 1 over square root of m here. Okay. Good. Now the question for you is, can the rate 1 over square root of m, can that be improved? Can we have a faster rate than that? So what do you think? Maybe not everyone at the same time. I pick you. No, you have to tell me.
Depends on F.
On F, yeah. And so what type of properties should matter?
Regularity.
Yeah, indeed. Yeah. So if we have more regularity, and the second thing is, it also there's a integral over theta. It depends also on the theta actually. So actually, what you can achieve is a better rate. So this 1 over square root of m, and you can get a better rate S over D, and the improvement S is the smoothness, what you said, the smoothness of the function that the interior function, which was called G before. So and the second one is notion of parameter dimension of the space theta. So if you have a large theta or a small theta, that then changes to dimension d, and then we can get better or worse improvements. So here, let me make this a bit more precise. So, right, the theta rule, we haven't applied this yet to neural networks, but we have g theta x d phi theta, right? So this is this theta over which we integrate. And so we can, like in cos-p dimension, maybe you have heard about this. So we take a covering with epsilon balls and some norm, say maximum norm or L2 norm, doesn't really matter. And then we wonder how does this bound grow as epsilon goes to 0. The smaller the epsilon, the more balls we need. So this will grow in the epsilon, and this will increase as the epsilon decreases. And then we wonder with which rate does it increase. And so that is then driven by this d. If we can establish such a bound with some d, then we can. This is the d that later occurs in the result. So it's basically the sort of measure of the dimension of this theta. If the theta is a 0, 1 to the d, or so, then you get just the d is this capital D. The second thing is a notion of the smoothness of. Here I already. Okay, so it's not entirely consistent. Here it's already for the activation function sigma, but this was before the g. And I also have now put these things in here. So I'm sorry. So this is already applying the previous result now to shallow neural networks. It's a bit cumbersome, so I just give you the main idea. So normally, if we think about smoothness, then smoothness we define it by the number of derivatives. But here we need to define it a bit in a different way, more like in the terms of quadrature rules or so. It means that for every parameter w and v, we can find in a neighborhood, we can find k points, capital K points. We can pick our k, such that we can represent that the activation function at that point by a sum over these k's. And the whole representation, the right-hand side is not allowed to depend on the this one, these wj, vj, they're not allowed to depend on w and v. In these number j's, the weighting, of course, that can depend on the w and the v. Such that we get approximation error epsilon to the s. Okay, so it's a bit like we have chalk. So anyway. If we have a smooth function, my pen also doesn't work anymore. Okay. No, we have a smooth function. This is our function sigma. So everything is one dimension, and then, for instance, this can be w1, this can be w2, and then here in the middle, if the w is in the middle. And I ignore these p's for the moment. If the w is in the middle, we can somehow write it as a linear combination of these 2 points, w1, w2, such that we get the approximation error epsilon squared or epsilon cubed, and that gives us then the s. So for value, you can show that you get s to be equals 1 actually here, with what you would expect, because it's Lipschitz smooth, so it should have exactly this property. And then the result now is the following. It says that okay, before had approximation in this spaces L2 Q for any measure Q, you can actually generalize it to type 2 Banach spaces. So that includes not only these L2 spaces but also everything in LP.
M minus 1/2 minus DOS.
Yeah, that's right. So this is the rate. Yeah. So this is the type as well. S over D. Good point. Yeah. So this is the rate. Yeah. Yeah. Do you agree?
No, I agree with S over D, but I'm a bit surprised by the fact. I mean, if you compare with standard non-parametric statistical rates, like the parametric density estimators,
yeah,
then you would have something like S of the numerator and at the denominator, so such that if S goes to infinity, you get n minus 1. Whereas here it looks like that with S super smooth, you can get something which is arbitrarily large in M.
Yeah, so probably there's some sort of saturation that that I think the S can never be larger than d over 2. The notion of smoothness that you have here, I believe that this somehow, if this in higher dimensions somehow it's not going to work anymore. So there must be something that if you define smoothness in this way, that there's some form of saturation in terms of the dimension.
You would expect that it can be larger than 1 over m.
If you have this,
it shouldn't be larger than 1 over m eventually, no?
If you think you can prove a lower bound of 1 over m, that's a good point. But those are integrals, right? So if this, I don't know if this, now suppose the theta would be supported on a discrete set or so.
No, but what you said before is fine in the sense that if S cannot be larger than d over 2, then you get m minus 1 half minus 1 half, and it's 1 over m, and that's reasonable. I mean, that's...
Yeah, but in principle, you could get better rates here as well than 1 over m. For instance, if the theta itself, right, so this theta here, if this is just if this is a probability measure that is just supported on one point, right, then you just need one unit to exactly represent that, so you get a perfect representation in this case. So yeah, maybe for one would have to specify like under which conditions can you get to 1 over m lower bound here. So that has also to do with the theta.
Really just like the sense is just a biased term. So you go.
Yeah, right. Yeah. So it's not yet there's no statistical.
This would be just a biased term, not a biased term.
Exactly. Yeah. So there's no sampling yet in there. Yeah. Still, we call it this sometimes the sampling because this is can be seen somehow from a sampling argument because this is the integral. This is somehow the population version also. And then we go to the Celler networks, which is a finite sum. And if you look at this Maury's theorem or so, then it occurs by sampling from the probability measure here in the integral. But it's also not true that indeed it cannot directly be linked to non-prime matrices. So we don't look at these function classes in non-prime matrix statistics. Okay, so here's say so you can do it for all these L2Q, and you can generalize it to more general notions like these type 2 Banach species. And so the result tells us, okay, if this is the object that we would like to approximate, then we can find a shallow neural network which has m hidden units, and that gives us this rate. And now, before we just had 1 over square root of m, and now we get this slightly improved rate with the S over d. Of course, in practice, if the parameter dimension is d is a million, right? If you have a very high dimensional object here, then this will not help you a lot. Right? S is equal to 1 for value, it's not better than 1. And so that the improvement is minor, but there's certain results where this actually matters. Okay? So there's one result where this tiny improvement helps you a lot later. Okay, so this is about how to approximate. So what have we done? We have now find a way how with the Celler network we can approximate these infinite width neural networks. And now we can look at the second stage. We can, like if we have a Lipschitz function, how we can approximate with a Lipschitz function by using functions of that form. And the good thing is the m is gone now, right? Because there's no m in here. So it's still approximation theory. It has nothing to do with statistics yet, but it simplifies the problem. And we can use other tools as well, which work on the integrals and not on the discrete versions. Okay, so let me briefly take you through this notion of approximation rates and approximation theory. So if we have suppose we have a function class calligraphic G that we of target functions we want to learn. We believe like the thing we want to learn the thing that underlies distinguishing cats from dog images is in a certain class, and this is calligraphic G. And now we are wondering, we take a function class that is parameterized in neural networks with capital N parameters, and we wonder how well can we approximate this. And the thing is that we look at the best approximation in our class for every element and then take the worst case over all these possible target functions, because we don't have any control of this. We don't know which one it is. The typical idea is to say, okay, so then let's work with the worst case scenario in this setting. And we are not interested now in exactly how this Rn behaves. We are just interested in, as the number of parameters, capital N goes to infinity, how fast does this go to 0? Because the more parameters we have, the more expressive this function becomes. So this should become smaller. These functions should also be nested. And if this becomes smaller, somehow the Rn should go to 0. And then we wonder, like, how fast does the Rn go to 0? And then we have, now if we go to approximation of functions that are defined on 0, 1 to the d, the typical approximation rate that most of these schemes have, these parameterized schemes, is n to the minus beta over d. And that probably refers to your question. So beta is the smoothness of the function. So here I just write beta smooth, but you can think about Helder smoothness. If you've heard about Helder classes, then think about beta to be the number of derivatives that this function has. So if beta has, if the function all have 10 derivatives, then beta would be 10. And d is the number of the domain on which these functions are defined. And there's this curse of dimensionality phenomenon. The larger the d, the slower these rates. It's harder, it gets harder and harder to approximate it. This has to do with the fact that if you're in higher dimension, then they are much, much larger, these spaces. So if you have like points, if you put n points in the d-dimensional space, 0, 1 to the d, then the distance between two, like the average distance between 2 points is n to the minus 1 over d. So that they become more and more empty. If you put n points, then they're far away in these high-dimensional spaces, and then you can, so neighboring information is very loose, right? You can use a lot. The functions could have between 2 points could have changed a lot, because they're further and further apart in higher dimensions, and that makes the whole thing to become harder in high dimensions. So you get this curse of dimensionality thing, which if you have think about these MNIST images where the input dimension is 784.28 squared, then this can kill any smoothness basically over here, such that you get very, very slow rates. And it's always the question how machine learning can avoid the curse of dimensionality. And I will come to this on Wednesday in the lecture. Okay, so now, and there's a second thing that happens if you take, I mean, we talk about approximation theory with function classes that are somehow parameterized in n parameters. If we take a class where the smoothness, I mean, there's smoothness on the class G of functions that we want to approximate. So here this beta refers to the function, the target function. We want to learn a 10 times differentiable function, and beta is equal to 10. But there's also smoothness of the functions that you use to approximate this, right? The neural network. What is the smoothness of the neural network that you use? And the thing is, if the smoothness of the neural network is small compared to the smoothness of the target function, then you can typically not achieve this rate anymore, because the mismatch is too big. And you can easily see that if you, for instance, think about the x square function again. So this is x squared, and this is infinitely often differentiable, right? So beta here, this should be infinity basically. And now as an approximating scheme, you take a piecewise, say in the first step, you take piecewise constant approximation. Okay, so you're allowed to put n parameters. That means you put n pieces basically, and you can adjust the height of the pieces or the locations, depending on where you put the parameters. The thing is, because the variation in each of these pieces is basically the size of the interval, and you can put n intervals on 0, 1, so the variation is 1 over n, so you get an approximation rate of 1 over n for this function x squared, and you don't get the rate which is much worse than the rate n to the minus, okay, so infinity and, right, so this over d. So that would be this would be the vertical rate that I showed you on the previous slide, beta over d. Beta is very, very large, like as large as you like. But because you take this rough scheme, piecewise constant functions, you only can get 1 over n rate, the saturation. And that happens here. Basically, if the true smoothness is for piecewise constant functions, the saturation happens for equals 1. Okay, so it's always the smoothness of the class, here the piecewise constant function is plus 1. So piecewise constant function have smoothness 0, and then you can add a plus 1. So continue like Lipschitz functions, you can still approximate to the optimal rate, beta to the d. But if it's twice differentiable, you can't gain anything more. Okay, so there's some sort of saturation that happens. Now, if you take instead piecewise linear functions and value functions are piecewise linear, then what happens in this case? Okay, so you can also approximate the derivative because you are piecewise linear. So you can do something, for instance, like this. So you already see in the way I plotted, or it's a very bad plot. Somehow it looks much better, this approximation, the orange one than the blue one, right? But also for piecewise linear functions, you have a problem because you only can approximate the function and its derivative, but not its second derivative. And so then you get stuck at beta equals 2. So you get, in this case, you get the rate 1 over n squared for the piecewise linear. And there's nothing you can improve. So it's still worse than n to the minus infinity over d, right? So e is equal to 1 here. So it's still, that has to do because beta plus somehow you have saturation. And now, the quiz question for you is for value in d dimensions, where is the saturation point? Okay, and maybe one thing is, okay, so I have just shown you this in one dimension. With these piecewise constant and piecewise linear functions, you will get beta plus equals 1, beta plus equals 2 in all dimensions d, so it doesn't matter. So think about a square or a cube if you can imagine it, but for a square I think it's quite easy. So you just split it up and put piecewise constants on each of these little squares, and then you approximate your function, and that's basically the best thing you can do. So you can see that you can't improve then the beta plus equals 1. So, and for piecewise linear it's the same thing. So now my question to you is, what will happen for value networks when up to which point can they achieve the good rate beta over d in the approximation, or can they at all? A different way to formulate it, what is the beta plus? So for the d equals 1, it's clear. Then we have just seen already beta plus is equal to 2. But now for general d, Domenico, now you have to come up with a guess. Oh, okay. Maybe it's related to your work, I thought, because what happens actually, there's a blessing of dimensionality effect here. So you would think actually that this is the thing, right? So you would also think in all dimensions from like standard approximation theoretic point of view, the guess would be it's piecewise linear value networks depending, even deep deep value networks are piecewise linear, but also shallow ones and so on, and so you can't go beyond the 2 here. But the interesting thing is that if d is larger equals 3, one can prove that you can get the good rate beta over d up to a beta that is of that size. So you see for d equals 1, it's 2, what we have seen before. If you have larger d, you can get better. And that's a really weird phenomenon. And I want to explain a bit where does that come from. Okay, so it's something which is really special about value networks. And the thing is basically that the value networks, they are piecewise linear. But what matters in the end is what we also have seen in this approximation that we have done before. So what matters in the end is very much like how these functions, these integrals, how smooth they are. And in these integrals, you have integrated over these values. And the higher the dimension, the more integrals you have. And that smoothes these functions out. So it's not why we think from a traditional perspective, we think, okay, the functions itself, the smoothness of the function itself is important. Now it's just the smoothness of these infinite width limits. And they are much, much smoother objects. And because they are smoother, basically, they can pick up better the smoothness of the target function up to this point. You can also, if you're maybe you know Radon transform, when I started a lot of inverse problems, and so you know that also Radon transform has this thing that's a smoothing operator, and it adds d minus 1 over 2 derivatives to the function that you represent. Okay, so you have a function, you pass it through the Radon transform. Afterwards, it gains this d minus 1 over 2 derivatives. It's a very similar thing. I didn't put the slide before that you like this thing people did for the universal approximation property to prove it via a Radon transform, which is also proof, but it's closely tied actually to what these shallow value networks or shallow networks in general do. Okay, so here I just want to highlight a bit where this comes from. So this is based on harmonic analysis. Okay, so I think in the internet the pictures. Oh no, it moves now. I see. Yeah, it moves. Okay. Okay, so we do that just on the sphere because then everything is easier, and I get rid of these biases. And one can, I mean, considering inputs on the sphere is actually something very reasonable also from a practical point of view. I know you also do that here in Rome. Also, sometimes people do some pre-normalization also before they inputs and normalize them in a way. There's a lot of theory as well that just works on the sphere. It allows us then to use the harmonic analysis on the sphere. Okay, so I just want to give you the rough idea because I don't want to spend also too much time on that. So where do these spherical harmonics come from? So you can first define homogeneous polynomials in D variables. These are polynomials in that form. You might have seen all this before. And so this is this multi-index notation. And so that means this the overall degree of this is in D variables. And so the overall degree here is the sum of alpha 1 plus alpha d. It has to be equal to k. With degree k. Okay. Now what we can do is we can restrict that to this domain, and then the polynomials that are homogeneous, they are called harmonic if the Laplace operator also vanishes. If they apply to the Laplace operator, then this vanishes. And if they are restricted to spheres, then they are called these spherical harmonics. And here are some two examples. And now, okay, so this is probably something you have also seen before. Then you can define the Laplace-Beltrami operator. This is somehow the spherical part of the Laplace operator. And it's known that it has these the spherical harmonics that were defined before are the eigenfunctions of the Laplace-Beltrami operator. And they have eigenvalues that depend on the k, which was degree, and underlying dimension d. So you see always something happens if d is larger than or smaller than 2. Okay, so this the dimension is here. Now, one thing you can do is if you have a function f, you can now it's a generalization of Fourier analysis, right? So it's spheres, and so one can define these spaces that are the linear spans of all these spherical harmonics with a given index k and d, and they are for different given d and different index k, say k and l. If k and l are different, then they are orthogonal linear spaces with respect to this inner product, where this is somehow the uniform measure, say on the sphere. And then any function that is in L2 on the sphere can be written as this orthogonal decomposition in this form. And the key thing why this is now relevant for neural networks is this identity here, this factorization property. Because what it says is that if you have a function that looks like this, and maybe let me write this out, and then you will recognize what this is. It's exactly like these. So this is a function h of x transposed. Maybe I should have called this W transposed, because to make better the link to neural networks, W transposed x g of x e tau of x. So this tau is this uniform measure on ST minus 1. Okay, so this is basically what we had for these infinite width shallow networks. And so here this h will be the activation function, right? And the g okay, I wanted to, okay, this was just the wrong way around. So this should be over the w, sorry. I just rename everything, so I can just call this w and this. Okay, so then it's better, right? So then you can better make the link to the infinite width network. Now this was before called, I think, phi. Okay, and so what happens now is, because this projection of these integrals, which are infinite width networks, they can be decomposed into a product where we have the projection operator, right? So this thing on the space of spherical harmonics with indices k and d of the function g times a quantity that depends on that part. Okay, so why is that so important? Because now you can, here in this step, you can decouple the influence of the activation function from the representation phi. Okay, so maybe I'm not sure how I wrote this. Okay, so maybe I add this here. So before we were looking at functions f of x, which looks like phi of w sigma w transposed x d tau w. There was a dp of w before, but we can somehow put the density, we can put that into the phi if we want. And now, if we want to understand how well this function f can approximate a given target function, say t, then what is very important is to understand what is the underlying, the only thing we can change in this representation is the phi here, right? Everything else is fixed. So we need to understand what is the phi that corresponds to a given x, that's like the kernel here that corresponds to that. And this is exactly what this formula allows us to do, because now here this is something that depends on the activation function and nothing else. We can compute this for values, so there's a formula which somehow involves also these Gegenbauer polynomials, but I just wrote it as a more explicit formula that depends on the sigma. And then the second part, it only depends on the phi thing. Okay. So
G is a function of the sphere.
G is the function, yeah. So everything is on the sphere now, yeah. And the phi or the phi here, yeah. Okay, so maybe I can show you how that now works. Okay, so we have our function f. Okay, so let me. Okay, so that this. Okay, I should have better prepared this part. Okay, so how does that work? Now we have. We want to represent a function. How do we call this? We have already taken all the letters here. Okay, so this is the infinite width network, and forget about that. This was also called G. Okay, so now we work with this formulation, and now we want to we go back to the original formulation of approximation rates, and we have a function g that lives in L2 of SD minus 1, and we want to approximate it by a function f of x that is of this form here. Okay, so that's the task. So we want find f.
The integral you wrote up there, right?
Yeah.
The g should be a g of x and d tau x, right?
Now we can just, so here I swapped, so here it was, I just swapped the notation to make it more comparable.
Yes.
So what was called here x is, maybe even it's the same as the x over here. Yeah. So this internal variable is called w here, so we integrate this out over the w. Yeah. I think it's okay, it's exactly like this. When I write the scalar product like w transpose x or x transpose w, that doesn't matter. Yeah. Okay, can I show you the trick, and then I think it becomes maybe more clear. Okay, so we want to find this such that g minus f in L2 SD minus 1, this should be small. Yeah. How do we do this? Now okay, I don't have included a, okay, I put it here. So we take our g, and then we write this as these projections kd of g. And we also know that the f, we can also write this, any f of this form that we have discussed before, we can write it like this, and this is the same, so those are sums over the k. This is the k as sigma hat k, projection k d of phi, right? Because this is exactly this formula that we had over here. Now this h is the sigma and the d is the phi, so we just use this formula over here. So this means now if I want to approximate this, the thing we can choose is the phi. Okay, so we can, for instance, now say, let's take another color. Okay, we set this because we can choose the phi. We choose this to be the projection of g times sigma hat k to the minus 1, or 1 over sigma hat k. Because if we do this, then this one cancels, and this one is the same as g. And then this will give us exactly g. So that means we can perfectly represent this function over here. But there is a problem with this, because now if we define it like this, then this phi cannot be an L2 SD minus 1 anymore. Or it can have the extremely large norm in L2 SD minus 1. So basically the thing is just to do that and to truncate up to capital M here, and then we just get this approximately, and then we have two parts in the approximation, the low frequencies where this is still acceptable to do that, and in the high frequencies we get the bias, which comes basically from the frequencies that we don't cover here by the f. Okay, so why can't we have the large L2 norm of the phi? Because we also had this other result that I showed you before, namely this one, which involves, right, so if we approximate this, we don't want to have a too large phi here, because let's say this is phi is infinite or so here, then we get also just infinity, so this will matter at some point. So in the overall approximation rate, this m that we have picked, this will come in here, because this will grow in somehow in the m. And here here we want to have a small m, because otherwise this will blow up. And for the other results, to do this trick over here, we want a large m, because the larger the m, the better f approximates our g over here. Right? So on these things, they go against each other, and in the end, there's a perfect m that trades off everything, and then we get the good rates. Okay, and so where does the trade-off come from? Well, here the important thing is to work out how these HZK, how they behave if we take its activation function, if we take the value. Okay, so then you can also see where all these things basically come from. So if you work out what are these numbers for their value, then you see that the odd numbers for the odd k, they all disappear, which is a bit problematic. Why is it problematic? Because in this argument here, if this is 0, then these odd frequencies for odd k, we cannot match them with this one. And so they can be large, and that can be very problematic. So you need somehow something which breaks the symmetry, which you can do by, for instance, introducing by these biases also later, which we, right? So this V, which we have ignored here. Okay, so that's a minor thing. And then for the even ones, we have an explicit formula how this decays, and one can show that the decay for large even ones is of this order, and that shows basically the smoothness in this domain, how much additional smoothness you get by using this value. And this is also known if you take value to the power alpha, you see exactly where all this happens, and that's and then based on that you can then prove. Based on this, you can then prove this result over here. Okay, so you put all these pieces together. You have to optimize over this capital M that I have shown you. If you put it together, you see that you have this delayed approximation saturation point for the approximation rate, which is a surprising fact for a value network. They don't beat the approximation rate, right? So that's not the thing. It's really that although you come with a rough scheme, piecewise linear functions, you can approximately relatively smooth functions. So this was a bit chaotic and messy. You have a question about this? But you're also all experts for harmonic analysis, so I probably didn't tell you so much new things. Good. I have just 1 minute left. So the last thing for this approximation theory are these Barron spaces that you have seen before. And maybe that's I don't know how this, I think the time is up. Maybe that's a good thing to start with this on Wednesday. And then the next thing I want to do is I want to go to these advantages of additional layers. So what we will see is that there are certain things like localization that you can do if you add hidden layers. We know that we have more efficient approximation of polynomials with deep neural networks. There's this thing about Kolmogorov-Arnold representation theorem. Maybe you have heard about Kolmogorov-Arnold networks, which are not there yet. They appeared on April 30 last year on arXiv, and they already have 950 citations. So this is a big thing nowadays. And then I want to zoom in and particularly talk about advantages of deep value networks.